If we want to understand electricity, first we'll have to take a look at atoms. They are made up of three types of particles: protons, neutrons, and electrons. A proton has a positive electric charge, neutrons have no electric charge, and electrons have negative electric charge. Protons and neutrons group together and form the dense and heavy nucleus of the atom. For comparison, a proton is about 1,800 times bigger than an electron. The tiny and light electrons swirl around the nucleus in a cloud in fixed distances called shells. The further away the electron is from the nucleus, the higher its energy level. The amount of protons and electrons an atom has tells you what element it is. Silicon, for example, has 14 of each, hydrogen only 1, and copper 29. There are 118 different elements in the periodic table, each with a different amount of electrons and protons. Since electrons and protons have opposite charges, they attract each other. Now you might ask yourself, if they attract each other, why don't the electrons move towards the protons and eventually collide with them? This is a fairly complex question that we'll leave for the realm of quantum mechanics, because it would go way beyond the scope of this video. The important thing to understand is that electrons can only be in a certain distance to the nucleus. These distances are called shells or energy levels. And there can only be a maximum amount of electrons per shell, and if the shell is full, it is stable, and those electrons will need a very high amount of energy to break away from the atom. The ones in the closest shell to the nucleus have the strongest attraction towards the protons. The electrons in the outermost shell have the weakest attraction towards the protons because of the distance between them, especially if the shell isn't filled up, and they can be pushed away from the nucleus by applying a force, and they will then drift from one atom to another. If an atom loses an electron, the positive protons will then outweigh the electrons, giving the atom overall a positive charge. The atom is now a positive ion looking for a new electron to fill the gap. The drifting of the electrons is what creates the electric charge and makes electricity possible. If you put a bunch of copper atoms together, you'll get a material made up of pure copper. Because the electrons from the outermost shells of the copper atoms move all around the material, copper is a conductor, meaning it can conduct electricity very well. The opposite of that, meaning materials made up of atoms without loosely bound electrons, for example plastic, are called insulators. Electrons can't move as freely in those materials, and they can't conduct electricity as well. These materials are often used to stop the flow of electricity, for example, wrapping an electric wire with them so that you won't get an electric shock when touching the wire. Even though the electrons in the copper wire all move around the material, there is no current yet. To create an electric current, the electrons need to flow in the same directions, which can be achieved with the help of batteries. A battery has a negative and a positive terminal. At the negative terminal, the atoms in the batteries have a surplus of electrons, and at the positive terminal, the atoms lack electrons. Since the atoms seek to be in balance, meaning they want to have the same amount of electrons as protons, if you connect them with a copper wire, then the excess electrons on the positive terminal will start moving towards the negative terminal to restore the balance. Contrary to popular belief, the electrons actually move very slowly at a rate of around 60 millimeters per minute, depending on the current, since they have to work their way through the billions of atoms, which will take quite some time. But since all of them move at the same time, the electric charge moves almost instantly. Think about it this way. If you introduce new electrons on one end of the wire, the electrons that were there before them have to make room for the new ones and start moving. If you would leave the circuit as it is now, the wire would heat up and maybe cause a fire, because the current is too strong. This is called a short circuit. To slow down the current, you can use some semiconductor material, which is a material that conducts electrons only partially. This will keep the wire from overheating, and now you have a fully functional electric circuit. The current will only run if the circuit is complete. If you cut the copper wire, the current will stop. Attach the wire back and the current will flow again. We can now build a simple switch controlled by a button that can turn the circuit on and off, which means we now have full control over the circuit and can turn it on and off whenever we want. But what's so exciting about controlling an electric circuit? If we put something into the circuit, like a piece of tungsten, which is a material that heats up quickly and emits light when current flows through it, we will get a light source, which we can control with the button. Or we can put a thin wire of copper into the circuit and wrap it around an iron bar. When the circuit is on, the electricity will produce an electromagnetic field that turns the iron bar into a magnet. And we can use this magnet to pull a metal onto a device that produces a sound. When we switch the circuit off, the magnetic field will disappear, the iron bar stops being a magnet, the metal jumps back into its original position, and the sound disappears. Now we have a circuit that controls a sound when we press a button. A pretty cool device. It's called a telegraph, and it was invented by Samuel Morse, among others, who also invented a system with which you can translate short and long sounds into letters, words, and numbers, so you can communicate with someone over long distances with just simple sound. Dots represent short sound and dashes long sounds. 3 dots, for example, represent an S, 3 dashes an O. SOS, a signal meaning distress, would be 3 dots followed by 3 dashes followed by 3 dots. If you want to send someone a message with this telegraph, someone who understands Morse code will have to be on the receiving end, translating the sounds into the English language. Let's go further and add another circuit with a switch, but this time we'll let the magnet of our first circuit control the switch of the second circuit. Let's also add a light to the second circuit that will turn on when the switch is on. When we press the button, the magnet pulls the switch of the second circuit, closing it, and the light turns on. When we press the button again, the iron bar stops being a magnet, the switch goes back in its original state, opening the circuit and switching the light off. Now this is the same thing we had earlier, just more complicated, since it basically does the same thing as if we were to replace the magnet with the light in the first circuit. But if we change the switch of the second circuit to be closed when our original switch is open, and open when our original switch is closed, we can invert the signal we give it. This is called a logic gate, and more specifically a NOT gate, because it outputs the opposite of what we give it. The input is the first switch, which is representable as a 0 for an open switch and 1 for a closed switch. The output is the light, 0 for no light, 1 for light. Let's go back to our first circuit and add another switch to it. You can see that the light will only turn on when both switches are closed. If only one of them is closed, the circuit is not complete. This is an AND gate because it outputs a 1 only when both inputs are 1s. If we rewire the circuit to look like this, the light will turn on if either switch is closed and also if both are closed. This is an OR gate. It will output 1 if at least one input is 1. You will often see these symbols for these 3 gates. And if you want to learn more about computers, try to memorize these 3 and visualize what they do and how the switches control the circuits to produce the outcomes in form of a light. These 3 logic gates are the most fundamental building blocks of a computer, and by using a lot of these gates in sequence, you can build computers that can multiply numbers, store values, or even play YouTube videos. You can't really overstate the importance of logic gates, and we'll spend a lot more time exploring how they work in future videos in this series on how computers work. So thanks for watching. I hope you learned a thing or two about electricity, circuits, and logic gates. My goal is to create a series of videos that explain computers, starting from electricity and ending with operating systems, browsers, and some more stuff. And if you have some feedback, please leave it in the comments below. Have a great day!